Hello students, welcome to Surface Chemistry part 4. In this part we people are going to study concept related to catalysis. Let us see thermal decomposition of potassium chlorate. Here you can see the thermal decomposition of potassium chlorate takes place at higher temperature of 653 Kelvin to 873 Kelvin. When the same reaction we carry out in the presence of small amount of manganese dioxide, the reaction takes place at lower temperature and even at faster rate. So here we used catalyst small amount of manganese dioxide, and here you can see that the temperature is reduced to 473 to 633 Kelvin, and it is also found that this reaction takes place at even faster rate. And in this reaction, whatever manganese dioxide we used, that increases rate of a chemical reaction without involving in the reaction, and it is called as catalyst. Student, what is catalyst? Catalyst is a substance that alters rate of a chemical reaction without involving in the chemical reaction, and finally it remains unchanged chemically as well as quantitatively. Once again, I repeat student, catalyst is a substance that alters rate of a chemical reaction, and itself it remains chemically and quantitatively unchanged after completing the reaction also. So what is catalyst? Substance that alters rate of a chemical reaction and remains chemically and quantitatively unchanged even after completing the reaction. That is called as catalyst, and this phenomena is called as catalysis. Question arises, how catalyst is going to increase the rate of a chemical reaction? For that we need to understand energy profile diagram of a chemical reaction. So let us draw a graph by taking potential energy along the y-axis and reaction sequence along the x-axis. Here we have reactants and average energy of reactants indicated, and products here we have. Okay, this is a energy profile diagram corresponding to the reactants in the absence of the catalyst or in uncatalyzed reaction. And from this graph it is clear that activation energy required for this reaction is very high. So this is the activation energy. But when I carry out the same reaction in the presence of the catalyst, so what catalyst does? It is going to provide me an alternative path of lower activation energy. Now you can see E dash is the activation energy in the presence of the catalyst and its value is low. So it provides an alternative path of lower activation energy, so that more and more reactant molecules now react and thereby forming the product. Hence, catalyst increases rate of a chemical reaction. So, how it increases? By providing an alternative path of lower activation energy. Students, now let us see some terms used in catalysis. First one is the catalytic promoter. Catalytic promoter is a substance that enhances the activity of the catalyst, that increases efficiency of the catalyst. Okay. For example, in the process of preparation of ammonia in Haber's process, iron is used as a catalyst and molybdenum is used as a catalytic promoter. That catalytic promoter increases efficiency of the catalyst, enhance activity of the catalyst. Once activity of the catalyst increases, its ability to catalyze the reaction, to increase the reaction, increases. Here iron is used as a catalyst and molybdenum is used as catalytic promoter. Now let us see catalytic poisons. See, catalytic poison is a substance. Catalytic poison is a substance that reduces efficiency of the catalyst, that decreases efficiency of the catalyst or decreases activity of the catalyst. So what is catalytic poison? It reduces activity of the catalyst or efficiency of the catalyst. The best example that we can see is in Rosenmund's reduction of acid chloride to aldehyde. So in Rosenmund reduction of acid chloride to aldehyde, palladium is used as a catalyst, and as a catalytic poison barium sulfate or quinoline is used. Okay, here we can see the reaction, acid chloride is reduced to aldehyde. The question arises, why we need to use the catalytic poison here? The students, if you not use the catalytic poison here, then palladium causes excessive hydrogenation of acid chloride, and thereby it converts acid chloride to alcohol as the final product. Actually we required the product aldehyde, but if you not use catalytic poison, excessive hydrogenation takes place and you get alcohol as the final product. To reduce that excessive hydrogenation, we are reducing the efficiency or activity of the catalyst by using the poison. So here reason is given, purposefully we are going to use the barium sulfate, so that decreases efficiency of palladium, thereby it prevents converting acid chloride to alcohol. It helps in converting acid chloride to aldehyde only. Now let us see types of catalysis. There are two types, one is homogeneous catalysis and another one is heterogeneous catalysis. In that one, the first one, homogeneous catalysis. Let us try to understand this concept with help of an example. The oxidation of sulfur dioxide to form sulfur trioxide with oxygen is carried out in the presence of oxides of nitrogen, that is nitrogen monoxide as the catalyst, in lead chamber method. Okay, so here in this reaction what happens? Sulfur dioxide is gas, students, oxygen is gas, and oxides of nitrogen, nitrogen monoxide is also gas. So all three present in same phase. So when reactants and catalyst present in the same phase, then that catalytic process is called as homogeneous catalysis. So what is homogeneous catalysis, students? When the reactants and the catalyst are in the same phase, then catalysis is said to be homogeneous catalysis. So example we already seen, that is sulfur dioxide, that is gas, oxygen, that is gas, NO, that is a catalyst, that is also gas. Both reactants and product are in same phase, hence this is an example for homogeneous catalysis. Now let us see some more examples. Acid catalyzed hydrolysis of ester like methyl acetate is once again example for homogeneous catalysis. In this reaction, students, you can see clearly methyl acetate is liquid, water is a liquid, hydrochloric acid or sulfuric acid you can use as a catalyst, that is also liquid. Hence both reactants and product are present in the same phase. So when ester undergoes hydrolysis, what we get? Carboxylic acid and alcohol, acetic acid and methanol as the product. One more example we can see, that is acid catalyzed hydrolysis of sugar, that is sucrose C12H22O11, that reacts with water. In other words, I can say it undergoes hydrolysis in the presence of sulfuric acid. Here also you can see that both reactants and catalysts are present in the same phase. This is also example for homogeneous catalysis. Students, now let us see the second type, that is heterogeneous catalysis. As the name itself indicates, in heterogeneous catalysis, the reactants and the catalyst are present in different phases. Okay, example is oxidation of sulfur dioxide to sulfur trioxide in the presence of solid platinum as the catalyst. So in this reaction you can see that sulfur dioxide, oxygen, they present in gas phase, whereas platinum present in solid phase. Hence it is an example for heterogeneous catalysis. Let us see some more example. Haber process of preparation of ammonia, where nitrogen and hydrogen reacts to form ammonia in the presence of iron as the catalyst. Here nitrogen and hydrogen are gaseous in nature, where iron is a solid. Once again this is an example for heterogeneous catalysis. Similarly, oxidation of ammonia in the presence of platinum gauze or platinum as catalyst in Oswald's process once again is an example for heterogeneous catalysis. Here ammonia and oxygen are present in gaseous phase where platinum is present in solid phase. Now let us see adsorption theory of catalysis. See, in the first process, students, first reactant molecules are diffused on the surface of the catalyst. Like this, we have unbalanced forces or free valencies on the surface of the catalyst. Now reactant molecules are going to diffuse on the surface of the catalyst. So these two are the reactant molecules, they get diffused on the surface of the catalyst by adsorption. Okay. Now in the next step there will be interaction between the reactant molecule takes place. So once these molecules are adsorbed, these adsorbed molecules undergoes interaction on the surface of the catalyst. So here you can see interaction between the reactant molecules on the surface. So first process, we have the catalyst in which we have unbalanced force of attractions or free valencies on the surface, which are the main reason for the adsorption. Now reactant molecules are get adsorbed here. Okay, so adsorption of reactant molecules on the surface of the catalyst, and once they get adsorbed, what happens, students? Interaction between these reactant molecules takes place, and that leads to the formation of product, and a product that gets dissolved from the surface of the catalyst to form catalyst as well as final product. So this is very simple adsorption theory of catalysis. Thank you, students.